Okay, so energy in a capacitor. All right, so we have a capacitor here, positively charged plate, negatively charged plate. There's a certain electric field between the two. So this is the electric field, E. And here's the potential difference between the two plates, delta V. Well, if you look at the picture here, suppose there are no other forces acting on a capacitor, in that case, once you let go of the plates will move towards each other. In other words, you're going to have kinetic energy, but kinetic energy cannot just come from nowhere. There has to be energy that is stored in this system to begin with, so that you can have kinetic energy eventually. So there must be potential energy, and this is what we want to determine. We want to determine what is the expression for potential energy. Now, suppose you take this little charge Q here that sits on this plate. This charge Q has a potential energy, and that potential energy is just Q times delta V. That is, if you let this charge go and it moves from one plate to the other plate, when it gets to this point, it will have kinetic energy, and that kinetic energy will equal to the potential energy, which you determine with this equation, and you have seen this before. So what we want to do is we want to add up all of these, the potential energies of all of these charges that are present here. And to do that, we'll do the following. d PE, or a little bit of potential energy, equals dq delta V, which gives me this, that the total potential energy is going to be the sum of all of these little parts of the potential energy from some 0 to some total, equals delta V dq, and I go from 0 to some total charge Q, where the total charge Q is just Q on a plate, whatever that Q total charge is. Now the expression for delta V is, let's see, this was C equals Q over delta V, and so what I have is Q over C. So then potential energy is Q over C. Oh, I see. What I need to do is, let's write little q, because I want to add all of them up, over C dq, and this is from 0 to the total charge Q. Now C is a constant, it's just the capacitance of a capacitor, and so that means that I can pull this in front, and this will give me half Q squared, and then I go from 0 to big Q. And so here's the expression for the potential energy. It's half Q squared over C. All right. Now, because I have also this expression here, C equals Q over delta V, I can manipulate this equation into other forms. So for example, I can get this. Let's do that. C delta V squared is one option, and then another option that I could do is half Q delta V. Let's make sure I got this right. Half Q delta V. Yeah, all right. So these are the three equations you could use for the potential energy of a capacitor. All right. Now, if you're in 1202, you can stop here. If you're in 1402, there's one more concept that you need to know, and that is energy density. So, energy density in a capacitor. We're going to define little u as the potential energy that you have in the capacitor over the volume of the capacitor. And we'll find an expression for the energy density. Note that the units would be joules per meters cubed. So the energy density would be, let's pick the equation that we need to get somewhere, half c delta v squared. Okay, so half c delta v squared is the one we will use, and we will divide it by the volume of the capacitor, and that's just going to be the area of one of the plates times the separation between the plates. So whether the capacitor is rectangular or whether it is circular or some other shape, doesn't really matter. It's the area of the plate times the distance between the plates. And let's substitute for the capacitance this equation, epsilon naught times A over D times delta V squared divided by A times D. A cancels. So what I have is that the energy density is 1/2 times epsilon naught times delta V over D squared. And this should remind you of something, namely the electric field, and so 1/2 times epsilon naught times the electric field squared. This is the equation for the energy density. And remember, units are joules per meters cubed. Okay.